Welcome again. In this talk, I will present the important concept of Nyquist condition. We will introduce the control problem, the requirement for closed loop stability, Nyquist analysis condition, and then Nyquist design condition. Why do we need control? To stabilize a process or a plant, to improve the speed of response, to handle uncertainties, to maximize profit, optimal control, etc. We will discuss the first three topics in this course. Here is a simple feedback control structure. Y is the actual value of the signal we are interested in, it is the output of the plant G. R is the reference signal or the set point. U is the manipulated variable or control input or control effort. E is the error signal, which is given as R minus Y, hence the name feedback control, because we are feeding back the output. V is the disturbance signal. We will consider changes in R and we will check whether the output Y follows R. This is the servo or tracking problem. We will also deal with problems that involve non-zero values in the disturbance V. We will refer to this as disturbance rejection problem. No matter what problem it is, we would need the closed loop system to be stable. Suppose we have a proportional controller along with our plant G. G is given as B over A. B is the numerator polynomial, A is the denominator polynomial. So the closed loop relationship between Y and R is given here. Kg over 1 plus Kg is the transfer function. If I substitute for G, it becomes B by A here, and I have 1 plus K times B by A. This is the closed loop transfer function times Rn. How do we design K? We would want the poles of the closed loop system to be inside the unit circle for stability. In other words, the zeros of the denominator to be inside the unit circle for stability. This is something that you have to remember all the time in this course. Now we will look at the encirclement criterion for stability. We would want the zeros of this factor which we saw in the previous slide to be inside the unit circle for stability. I have drawn the unit circle here, hence we will choose C1 as the unit circle. Recall C1 we discussed in the Cauchy's principle. Because we want the zeros of this factor inside the unit circle, we would choose the unit circle as C1. So here is the unit circle, and C1 is taken in the clockwise direction. Once again, ignore this cross mark here. So now let 1 plus Kb by A have a total of n zeros and n poles, including those at infinity. Let there be z zeros outside the unit circle. You have to remember this capital Z is the number of zeros outside the unit circle, and hence n minus z will be inside because there is a total of n zeros that this factor has. Similarly, let this factor have p poles outside the unit circle, and hence n minus p inside. For stability, we would want capital Z equals 0. What is Z? It is the number of zeros outside the unit circle for which factor? It is this factor. Okay. Remember, this comes as the denominator of the closed loop transfer function, and hence we would want this factor to have no zeros outside the unit circle. You would want no unstable zeros of this factor outside the unit circle. That is the same as saying our closed loop system does not have any unstable poles. Now How do we use the Cauchy's encirclement criterion? Evaluate this factor 1 plus kb by a along C1. C1 is a unit circle, remember from the previous slide, and plot it. That is imaginary of this factor versus real of this factor at every point Zi. Do this for the entire curve C1 and the resulting plot will be called C2. You have to remember this, so I call it C2, I have marked it in blue. What is Cauchy's condition? C2 will encircle the origin n times, where n is equal to number of zeros inside the unit circle minus number of poles inside the unit circle. Remember, however, that we have chosen capital Z to be the number of zeros outside the unit circle, so that is the reason why we have to subtract this. So this will be the number of zeros inside the unit circle, this will be the number of poles inside the unit circle, and this condition comes from Cauchy's principle. And when I simplify it, I get p minus z times. And recall that we wanted z equals 0 for stability, that is n equals p, because if I substitute z equals 0, I get n equals p for stability. And what is p? P is number of unstable poles of this factor, which is nothing but, I simplify this, so it is a plus kb by a, which is the same as number of unstable poles of b by a, because these two factors have the same denominator and hence the poles of this factor are identical to the poles of this factor. So we conclude that p is the number of unstable poles of a of z. But remember where b and a come from. They come from this factor, and hence we conclude that this p is the number of open loop unstable poles. A is the denominator of our transfer function g of z, and hence this capital P is the number of unstable poles, and hence p is the number of open loop unstable poles. And for stability, n should be equal to p or the number of open loop unstable poles. This is an important condition that we have derived using Nyquist plot. Now we want to pose it as a design problem for k. What do I mean by that? Let us recall that we evaluate 1 plus kb by a along the unit circle C1, plot C2. So here is the curve C1, we plotted it and got C2. C2 should encircle the origin p times, where p is the open loop unstable poles. But in order to plot this C2, we need to evaluate this factor at every point on C1. In other words, I need to know k before I can plot C2, but we do not yet know the value of k. Okay? If we know k, we can calculate C2, plot it and figure out whether the closed loop system is stable. But the question is, can I use this method to design k, to determine k? Thus whatever we have done so far is an analysis problem. Given k, Nyquist plot is explained. So we want a design approach to calculate k, which will be explained in the next slide. So because we do not know k yet, let me first subtract 1. So we will plot k into b by a along C1, I will call it C3. Remember C2 came from plotting only 1 plus kb by a. Now I am going to subtract 1 from every point here. So I get this new curve as C3. This is also plotted in the f plane, imaginary f versus real of f. For stability, the plot of kb by a, that is C3, should encircle the minus 1 comma 0 point p times. Remember, in the previous slide we said this C2 should encircle the origin p times. Now we shifted this whole thing by subtracting 1, so we should shift the origin also by 1. In other words, we should look at the encirclement of the point minus 1 comma 0. So for stability, the C3 plot should encircle minus 1 comma 0 point p times. Of course, we still need to know k, because I am saying evaluate kb by a at every point on C1. So how do we get rid of the effect of k? It is very easy, just divide this whole thing by k. So now we evaluate b by a along C1 at every point on C1, evaluate b by a and plot it, plot the imaginary versus real. We will call the resulting curve as C4. So we should divide this point also minus 1 comma 0 point also by k. So for stability, C4 should encircle this point p times, and what is p? Remember that p is the number of open loop unstable poles. C4 is the Nyquist plot. P is the number of open loop unstable poles. I would want you to go through this presentation once again. Note down what C1, C2, C3 and C4 mean. We will generally call C4 to be the Nyquist plot. Sometimes later in the course we might call C3 also as the Nyquist plot, but the context will explain. The condition that we take from this lecture is that the C4 curve should encircle the point minus 1 by k comma 0 p times, where p is the number of open loop unstable poles. In the next talk we will use this and design a proportional controller. Nyquist plot is extremely important. I would strongly encourage you to go through this and understand the principle behind it. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.